Good evening, everyone. And once again, on behalf of TERI School of Advanced Studies and the United Nations Environment Programme's Little Book of Green Nudges initiative and the Youth Education Alliance, I extend a very warm welcome to all of you. We thank you for taking out time to join us for the two-day workshop on building sustainable campus. Some of you, almost about 75 of you, made it yesterday as well and was part of this training session wherein we covered water conservation and rainwater harvesting and sustainable food on campus. Today we are going to yet another two very important features when we look at green initiative. One is energy and the second one would be waste management. So the first 1 hour would be for energy and especially focusing on renewable energy. We have for the session, we have Dr. Aviruch Bhatia, who is Assistant Professor in the Department of Sustainable Engineering at the TERI School of Advanced Studies. Amongst many expertise that he has, his expertise also lies in green buildings, and we have been using him extensively as a resource person for most of our training programs where we are looking at transition towards green building, not just building new green buildings, but also how could existing buildings may include green features, or how without really going for green building certification, you could still be green. So over to you, Aviruch. Thank you so much for joining us today. And you may please begin your session. We can see your screen already.
Thank you, Dr. Bhatia, for the kind introduction. So today, good evening all. And here today our topic is energy efficiency and renewables for the campuses. And here is the outline of today's presentation. So I'm going to just give the introduction about the topic, then building energy different end uses. So what are the end uses where building consumes energy, and how it is related to our climate and thermal comfort, and what are the energy efficiency measures that are possible in like in lighting system, equipment system, or heating and ventilation system. And then we will come to on-site renewable energy sources. Then I'll discuss in 1 or 2 slides net zero energy building. Then we will come to the conclusions. So here is a chart of total energy consumption, electricity consumption in different sectors. So here you can see buildings are the second largest component in terms of electricity consumption. And if you want to reduce GHG emissions, we can give focus to buildings, because here is a good opportunity where we can do the small changes and we can save a lot. So here is a second largest component. And if we
I'll request you to go full screen in the slideshow mode.
Okay. So and here are the different end uses where we consume energy in buildings. So you can see here we have lighting system, we have equipments, and large chunk of power that is consumed in ventilation and the air conditioning system. So we can see here about 50% energy that cooling and fans, that is our HVAC, heating, ventilation, air conditioning, where energy is consumed. And why the HVAC percentage is large and why it is continuously increasing? This is because the intensive use of air conditioners, because ambient temperature is continuously rising, our changes in the comfort culture, behavior, our expectations, improvement in living standards, increase in building internal loads, adoption of universal style of building that does not consider climatic issues. Okay, so these are the reasons. That's why energy in air conditioning increases, and the large chunk of energy is air conditioning, because if we compare, lights are there, equipments are there, these are small portions. Like if you have the T12 tube light, this is just 60 watts, fan 60 watts, or LED lights are there, small 10 to 20 watts, but air conditioners having the large size, it's about 2 kilowatt, 1.5 kilowatt. So if running hours of air conditioners are more, energy consumption is obviously more, and it's about 50%. So what are the strategies that we can adopt to save energy? So one thing is go for the passive solar technologies, where so that are the most efficient and the cheap alternatives. So passive solar strategies are where we are cooling or heating our building without use of conventional energy sources. So we are using the solar passive architecture. These type of strategies can be used, and also the passive and hybrid cooling systems and techniques can be used here. And to study the energy consumption here, study of the climate is very much important. So an analysis of the climate of a particular region can help assessing the seasons or periods during which person may experience comfortable or uncomfortable conditions. And the study of climate further help us in identifying climate elements such as well as their severity and that cause discomfort. So solar radiation, ambient temperature, air humidity, precipitation, wind, sky conditions, that are the variables that affects the climate. And India is divided into 5 basic climatic zones. So you can see here hot and dry climate zone, warm and humid, composite, temperate, and cold. So different strategies can be chosen in the buildings as per the climate zones. Like if you have the hot and dry climate, so evaporative cooling can work better. Warm and humid, we have different kind of conditions, temperate, cold, composite climate. So these climate zone classification is done on basis of mean monthly temperature and relative humidity. Thermal comfort is also one of the aspects. It is very good related to energy. And here is the from ASHRAE, American Society of Heating, Refrigeration, Air Conditioning Engineers. 55 is the standard for thermal comfort, and thermal comfort is the actually condition of mind which expresses satisfaction with thermal environment. So, and there are mainly these 6 variables are there on which thermal comfort relates. So these are the metabolic rate. It depends on our activity, what activity we are doing, clothing insulation, air temperature, air velocity, mean radiant temperature, and humidity. And this thermal comfort is not possible to satisfy all the people in room. So we generally prefer for 80% or 90% people are feeling satisfied, that is fine. So here is the table how there are many studies how thermal comfort depends also on mean monthly outdoor temperature. So you can see here in Stockholm or Armstrong, where mean monthly outdoor temperature is less, like 16 degrees Celsius. So their thermal comfort ranges are here from 19 to 24 degrees Celsius. But in India, where we have the mean monthly temperature higher, about 34 degrees Celsius. So we can feel comfortable at even 25 to 31 degrees Celsius. So it is not necessary for us to maintain air conditioning temperature as 22 degrees Celsius or 21 degrees Celsius. We can feel comfortable because our mean monthly outdoor temperature is higher. So if we can set our air conditioning system at higher set points, like at 26 degrees Celsius, let's say, we can feel comfortable. So one strategy is we can maintain the higher set points and switch on ceiling fan, because we have seen out of the 6 variable, wind speed is also one of the variable which we can control comfort conditions. So if we can set our set point at 27 degrees Celsius or 26 degrees Celsius air conditioner, and if we run ceiling fan at small speed, at low speed, then we can feel comfortable. And the government of India BE also notifies the set point, default temperature set point for the AC is 24 degrees Celsius. Now, when we switch on AC, it will start at the 24 by default. It is not like if you set 21, 22 degrees Celsius and we switch on again. So it is 24 degrees Celsius because in India, because of the mean monthly outdoor temperature is higher, our comfort requirements are different. And other strategy can be used as a thermal mass and insulation. So if thermal mass means if we are using like a stone structure, so it is applicable for hot and dry climate and composite climate. So if you have the stone wall structure, so what happens when outdoor is the higher? Let me explain you with pen. So in this chart, okay, so here x-axis is our time scale. So this is like 7 AM to next 24-hour each hour time scale, and on the y-axis we have temperature. So generally, if we see outdoor temperature, so this is the outdoor temperature swing. We get the peak about 3 PM, 2 to 3 PM, and then it will outdoor temperature is decreasing. So if we use thermal mass system, so what thermal mass does, at the outer side it will store heat and it will not allow to heat come in. So you can see the swing of the temperature in indoor temperature swing is like this blue line. So when outdoor peak is at 2 or 3 PM, if we are using thermal mass, it will store heat continuously and it will not allow peak to come in. So this peak will come in, let's say about 1 AM in night. So when outdoor temperature is already less, and it will again re-radiate outside, it will re-radiate the temperature outside. So we will get some time lag, and there is also a decrement factor. So if we use thermal mass or insulation, so we can reduce our burden on cooling and heating loads both. If we use insulation, it is specially for heating loads, and thermal mass insulation both for cooling loads. So that's why in older buildings, if you can see in like forts in Rajasthan, it's a stone made of the stone, and we can see the comfortable condition inside, even in the peak summer conditions. Other strategy is solar control and shading design. So here you can see if we provide kind of a solar shading devices on fenestration of building on the glass. So if we can cut down the solar radiation that is coming, we can cut down the cooling load for the building, and we can save a lot of energy. And we can also use the trees for this. So you can see the trees cutting in summer, sun is the higher side, altitude is higher, so it is able to cut. And the winter generally sun's altitude is lower, so on the south further we can get radiation inside. So here you can see the solar control and shading design in TERI SAS campus. So we have here, it's a glazed wall, and you can see the shading at a particular tilt. So it will not block the visibility. You can see outside, the views are there, but it is restricting the direct solar radiation that is coming inside. So we are able to cut the load, cooling heat load that is coming. So hence the air conditioning energy, and also there is a light levels, illumination levels are available inside for the working. So we can save on the interior lighting system also. So this is one more building. You can see here the shades are designed at a particular angle to cut solar radiation. And these strategies can be helpful to bring more and more hours in comfortable without switching on air conditioning system. So here you can see it's a chart. We generally call it the psychometry chart. Here x-axis is the dryable temperature, so normally outdoor temperature, ambient temperature we have, and this is the humidity ratio, and the curved lines are the relative humidity lines, because our comfort These are the two main variables, the dry bulb temperature and relative humidity, and we can plot it here. So each hour temperature is shown as a dot on this chart. So if there is a one dot here, that means its temperature, you can check it on the x-axis, and relative humidity you can check it on the these curved lines. So you can see here in Jodhpur, Rajasthan climate. So 10.7% hours are already in comfortable range when we don't need air conditioning or the heating system, and we can bring about 56% hours in comfort range without using any active air conditioning or heating system, by use of sun shading, if you are properly using blind control or shading devices on fenestration, high thermal mass, and night flush, direct evaporative cooling. These measures if you adopt, so you can see these boxes are the comfort ranges. So if any point is in this range, that means it is a comfortable condition. So by default, it was a very small area, but we can bring it more and more hour in comfortable range using these passive strategies and techniques. So here is the chart for Chennai. The same chart is prepared for Chennai. So here you can see because of the high relative humidity conditions. So compared to Jodhpur, temperature of Chennai is less, but humidity is high. So we feel discomfort. So you can see Jodhpur temperature is higher side, 40 degrees Celsius and more, 40 it is there, but relative humidity is less. So we can bring these hours in the comfort range. But in Chennai, most of ours temperature is not that much high, but relative humidity is higher. Still, here high thermal mass won't work, but still solar shading can be a very good strategy for energy efficiency. Similarly for Bangalore, so Bangalore is already, we know it's comfortable conditions. So with use of the different passive strategies, we can bring about 77% are in comfortable range. And selection of the glass in building is also very important. And in the existing building, we can adopt this strategy. So if we replace single pane of the glass with the double pane or triple pane glass, we can save good amount of energy. And there are the three important parameters for glass are the U value, that is related to thermal transmittance, and solar heat gain coefficient, and visible light transmittance. So any glass we need to we can choose with is having the higher VLT, visible light transmittance, because we want visible light to come in. In Indian tropical climate, we want visible light to come in, but we don't want heat to come in, because else we need to do cooling with use of air conditioning system. So we need to choose a glass where SHGC, the solar heat gain coefficient is less, but visible light transmittance is higher. So you can see here the solar energy distribution, the chart. So you can see here we have about 44% visible light, 48% is the infrared region. So if we are using normal single glazed glass, one single pane glass, so with visible light, we also getting 48.7% infrared region radiation. So this radiation is causes heating inside. So glass should be selected in such a way we should be getting more and more visible portion. We should be able to cut these infrared radiation that is coming, so we can block heat. So we can use the high performance double glaze or triple glaze glazing for that. Nowadays, to reduce the U value of glass, we can also fill in the inert gases, or we can create a vacuum between the panes to increase the energy efficiency of a building. And window to wall ratio is also important parameter. So we in India, if we want to design building, we should not copy the architecture or the buildings that design in the Western, like America or Europe. So we need to limit the glass on building, because in Indian climate, if you have the more glass, then that means we are getting more and more heat inside the building, and to control that heat, again we need to run air conditioning system, so that we are wasting energy. So here very much important thing is to find out what is the right size of the window glazing, the percentage of the window wall. So window to wall ratio is the wall area, the window area divided by window plus wall area. That is the window percentage on wall. So here I have performed one energy simulation with 3 different glass. So if I use a single glaze glass or double glazed glass or American Society of ASHRAE 90.1 code glass. So you can see if we are not providing glass, then also energy consumption is high, because if we are not providing glass, that means we don't get daylight inside. We need to switch on interior lights every time. So there is a high consumption. But when we increase ratio of the glass windows on building, so we will get the daylight inside the building, and our requirement for internal lighting, internal artificial lighting, will be the less. So you can see the energy consumption curve will go down, but after a certain percentage. So it is about 10 to 30%, depends on the building type and the design. And again, if you increase window area on your building, so your energy consumption will go high, because whatever till this point we are able to utilize all daylight that is coming inside, and we are switching off or dim our lights, interior lights, and we are using daylights. But if your window wall ratio is higher glass area, that means you are getting more and more heat inside the building. So you will get the curve like this. So it's better to optimize your point. So it is about 10 to 30% glass if you provide on buildings. That is well enough, good enough to get sufficient daylight levels inside building, and minimize our or optimize our energy consumption. So here is the window to wall ratio and glass type in energy conservation building code. So in India we have energy conservation and building code, where we have the different properties for the building components to choose. So here you can see we also have this for north latitude and the maximum SAGC non-north, because one important thing is we can provide more glazing on the north side, because in north side of the building we don't get direct solar radiation, so we can utilize the diffuse part of the light. So if we provide the more glazing toward north, it is a good, and it is not advisable to provide more glazing towards east and west, because east and west will get the perpendicular radiation, and that is very difficult to control. In the southern part also we can provide glazing, because in the peak summer sun altitude is quite it's high. So if we provide the overhang, so glass with overhang on the southern facade is also fine. But in the if your latitude is less than 15 degree north, so if we are designing a building in Bangalore and Chennai, then sun will also go towards north. So we need to control SAGC there. So you can see here, if in Delhi north facade we can provide a more solar heating coefficient, but in the southern part of India we need to still use the lower SAGC of glass. And the maximum allowable window to wall ratio is the 40%. They have kept it to 40%. So in energy conservation and building code we have two type of method. The one is the prescriptive method, and the one is the whole building performance method. In prescriptive method we need to follow the things that is written on code, and we cannot trade off the things. Much trade off is not allowed, but in other method we can do the trade-off between the different components. So you can see here 40%, if you are going with the prescriptive method, 40% is the cap. So window to wall ratio is lower than 40% is required. And daylight design is also an important aspect for the energy efficiency of building, sustainable, and daylight also provide the aesthetic and the human performance, increase the human performance. Our psychological and biological benefits will get. So here you can see a classroom with the well daylit classroom. So there are a number of studies in United States that claim the relationship between the daylight and the enhanced student performance. One major study analyzed test score more than 21,000 students in 3 school districts of California, Colorado, and Washington. So students in classroom with most daylight progressed 20% on math test and read 26% faster in the reading test. So you can see the effect of daylight. Even there are many studies in the hospital building and different kind of building. So if you have the well lit building, then you are saving on energy, your aesthetics is good, and you are also getting the benefit of the psychological and biological benefits. So there are less sick people, and so you are able to utilize the work performance of workforce. And if you want to reduce energy consumption in the lighting system, so we can use efficient lighting fixture instead of going for T12 tube lights. We can use the LED lights. We can also utilize daylight controls. So with the daylight controls, it is nothing but it is having the illuminance sensor. So what are the lux levels, illuminance level we are getting on table, and we can measure it, and we can dim the light accordingly. So if we are getting daylight levels, natural light levels on desk, so it is we can switch off or the dim interior lights, so we can save. So our if building is properly daylight design and we are getting uniform daylight levels, we can switch off interior lights. And we can also use occupancy sensors for to increase the efficiency of lighting system. So occupancy sensors will detect if there is occupancy in room, so lights will be on. If there is no occupancy, lights can be automatically switched off. So we can save good amount of energy. So here is one study. I found energy saving on university building using motion detection sensor and room management system. So you can see here, here about average 32.4% energy, average daily electricity consumption is saved with the use of motion sensors, that is occupancy sensors. Other strategy is a very cheap strategy is the cool and the green roof. If we just paint our buildings, schools building with the white paint, or if we grow some kind of greenery there, so we can reduce energy consumption inside the building. So here term refer to the material chosen to reduce roof temperature by increasing roof surface reflectivity or controlling temperature by other means of choice of material engineering design. So what happens if our roof surface is a dark roof? So whatever incident solar radiation is there, it absorbed, and it will conduct, because this is a roof slab, and if it is not properly insulated, so in India generally most of roofs are not properly insulated. So the heat, it will conduct inside the building, and it will increase your load and decrease the thermal comfort conditions. So, and you can measure in summer conditions when the outdoor temperature is 45-46 degrees Celsius. If you go and roof, your roof temperature will go about 70 to 80 degrees Celsius. So it's very heated, very warm. So if you use cool roof, just paint the outer surface with the high solar reflective paint, what happens? The most of solar radiation will reflect, and your roof will not be warm that much. And there is one more property of this high SRA paint is a high emissivity. So if you have the high thermal emissivity of material, so the high emissive material means if it can quickly absorb heat and it can quickly release it. So outdoor temperature is 45 degree and roof temperature is, let's say, 60-70 degrees Celsius. So it will quickly release heat outside. So the two properties are important. One property is reflectivity and other is emissivity. So here you can see the applications of cool roof. So here is one study I found, the Jilla Parishad High School. So it is a government school in Andhra Pradesh. So this experiment was done. So there were two blocks, classrooms. So one block is painted with the white high SRI paint. You can see in this Google image. Another block is normal gray color roof is there. And other experiment was performed in Nagpur. Valmiki Nagar Hindi Madhyamik Vidyalaya. So you can see here one block is high SRI paint, other is left as it is. So they found, because this is government school and it was not air conditioned, so here thermal comfort is important. So it was found that just by painting this white paint, high SRA paint on roof, they were able to reduce indoor temperature by 3 to 5 degrees Celsius compared to other other room that is non-white. And you can also see here on Jodhpur city, because it is in a hot and dry climate, very hot region. So most of houses are painted in the white in color. Roofs are also in white in color to reflect the radiation. And it is not necessary to use the very costly.
Here's a result from search.
Very costly paint. We can use just the China mosaic tiles on the roof. They're white in color to reflect solar radiation. And here is the one more study you can see here with paint of cool roofs on building compared to grey roof. So this experiment was performed. Two identical buildings were there. One building painted with the roof white paint, another building roof normally grey. So here we can see about 15 kilowatt hour per square meter, about 5% of air conditioning energy was reduced. 5% total energy is reduced with use of cool roofs. Now, reducing consumption of equipment and appliances. In equipment and appliances, we can switch off. The best thing is switch off or enabling power down mode to reduce energy consumption. Heat produced by equipment, which in turn lower cooling cost. Upgrading existing equipment, some energy efficiency appliances may cost more to buy, but recoup the saving in the lifetime of the equipment. So if you are purchasing energy efficient equipments, it might be initial cost is higher, but on the lifetime uses, it will use the less energy, so you can reduce your operating cost. Matching the equipment to task, bringing in the mind current and predicted requirement, taking advantage of energy labeling schemes. So we have now B star labeling, so 1 star to 5 star. If you are using 5-star rated appliances, more energy efficient. And the reducing energy consumption in equipment appliances. So it is necessary to, whenever we go, we should shut down our computer. So you can see here a computer left on overnight for a year creates enough CO2 to fill double-decker bus. So it is a standby power or ghost power, we can say. So it is, if you are not using and it's consuming some power. So if there are 100 computers and each computer using 1 or 2 watts, it's a lot of power is getting wasted. Similarly, the other photocopier machine. Now this was the part for energy efficiency. Now we'll come to on-site renewable energy. So renewable energy and related technology relevant to built environment include first is energy and other is the thermal, that is hot water system. So energy, we can use the photovoltaic system. It can be building integrated photovoltaic system or wind turbines. And for the hot water, solar thermal system or ground source heat pumps are there. In solar photovoltaic system, we can have it standalone and we can have the grid connected. So in standalone system, it is not connected to grid or off-grid system, where we have PV modules and we have DC to DC regulator, and we can use inverter if we have the AC load. And we because the solar photovoltaic, we don't it also dependent on the outdoor solar radiations. So if any storage is required, then we need to use battery for the storage. Other type of system, we have the grid connected photovoltaic system. So where grid is present and not many power cuts. So here we are not using any storage system. We have photovoltaic, we have inverter, and this power is supplied to building and it is also supplied to grid. So we have a meter, net metering system. So here is one example of grid connected photovoltaic system that we have at our university, TERI School of Advanced Studies. So we have 48 kilowatt rooftop system, and it is generating 60,000 kilowatt hours in a year, and we are able to meet 10% of the power needs of the building. And here is the one-day typical power generation on January 12, 2020. So this 48 kilowatt, we were getting the peak about 30 kilowatt we are able to generate in winter conditions. And other system, grid connected system, where we can use battery for the storage. So if there are several power cuts, so there is a one problem that if we have the grid connected PV system, and if there is a power failure in grid, then we are not able to utilize whatever energy is generated. So we can use the batteries to store that energy. And there is a concept of net metering. So we can get grid electricity, and whatever excess power we are generating, it is again sent back to grid. And here is the how much typical area we need, roof area need, if we want to install photovoltaic system. So here generally thumb rule is that 1 kilowatt PV system, if you want to install, we need about 10 square meter or 100 square feet area. So it depends on, it's a very rough number, it depends on the efficiency of the system and what manufacturing different properties. But thumb rule is that if we want to install 1 kilowatt of PV, then we need about 10 square meter, or in other units 100 square feet of the area. And if you want to calculate approximately how much we can get the energy generated from photovoltaic. So here is the solar resource map given by the NREL, National Renewable Energy Laboratory, USA. So you can see the different ranges in kilowatt hour per square meter per day. It is given in the different colors. So let's say if our incident radiation is 5.5 kilowatt hour per square meter per day, and we have the total 200 sunny days, so we can get about 1100 kilowatt hour per square meter, and let's say efficiency of the system is 15%. So our energy generation will be 165 kilowatt hour per square meter per year. And generally, sorry, this is written energy, but this is the area. So 1 kilowatt photovoltaics, we need about 10 square meter area. So this square meter, I am replacing it now kilowatt. So if I install 1 kilowatt of photovoltaics, then I can generate about 1650 kilowatt hour in a year. So this is roughly about 1.7 megawatt hour per kilowatt per year. But this is a ideal number, but actual generation will be the less. Like in our college, we are able to generate about 1.3 megawatt hour per kilowatt, because you need to clean the photovoltaic system, because if there is shading, then there is a loss. There are so all things. This is a very rough calculation that I have shown to you. And here is a benchmark cost by the Ministry of New and Renewable Energy. So this document is available on Government of India website, and I accessed in October 2021. So you can see the 1 kilowatt grid connected rooftop solar system cost is about 46,923. If you are going for the higher kilowatts, then it's less. And it's also depend on the different states, and different states have their different subsidies available. So here is the on the same website, solar rooftop gov.in rooftop calculator is available. So you can calculate the PV size based on the area available on the roof, or what capacity you want to install, or what is your budget based on that. So if I am selecting, let's say 20 square meter, that is let's say 200 square feet. 1 square meter is 10.76 square feet. So 20 square meter space is available, and I have the 50% roof area I can use, let's say, for solar power PV installation. And if state and city of Delhi institutional building is there, electricity cost is there. So these parameters, once you input and click on calculate, you can see here average in solar irradiation is the 1.156 kilowatt per square meter. So 1 kilowatt solar rooftop plant can generate 4.6 kilowatt of electricity per day. And so 1 kilowatt here you are the cost is the 46,923, and annually you are able to generate 1.38 kilowatt hour per year for 1 kilowatt. That we ideal calculation we did for 1.7. So throughout the lifetime 25 years you will be able to generate about 34.5 megawatt hours, and these are the tariffs. These are the tariffs is there available finance calculations. So in GRIHA rating system also for the existing building there is a credit. So if you are providing renewable energy for building, then there is a credit. So the percentage offset for daytime occupied commercial building. So 2.5% of total energy consumption for the existing building, if you are offsetting by renewable energy system, then you will be able to get. So this is a mandatory. So this is if you want to go for this existing building rating system, then this is a mandatory 2.5% energy you need to offset with the EV system. And if you are offsetting more, then you will get the extra points for that. So this is for this is based on energy consumption. So one thing is the energy demand, that is installed power. So that can be, so there are a lot of electrical load calculators are available. So if you have the all informations, so how many LED lights. So when I clicked on this Maharashtra discom.in, I got this calculator where these quantity already filled I got. So by default you can actually make changes if you know, but if you don't know you can use the default values. Then how many appliances you have, it will automatically calculate how many wattage is required. So in this, if you have campus like 25 LED lights, 10 tube lights, 5 ceiling fans, refrigerator, exhaust fan, computers. So 15.13 is a kilowatt is the installed power of this site. But for the achieve this GRIHA rating, it is not on installed power. It is actually based on electrical consumption. So for lighting, tube light, and all these, if you multiply by number of hours working, you will get the kilowatt hour. But for air conditioning system, it's not that much easy because air conditioning system efficiency also depend on the outdoor temperature and the inside conditions. Now here is the one thing, whether we should choose energy efficiency or renewable. What should we, whether we should focus on the energy efficiency or we should focus on the renewable. There is always like, so we can calculate actually payback. So if we apply any energy efficiency measure, so let's say if I replace my single glazed glass with the double glazed glass, how much extra cost I'm paying and how much energy I'm able to save annually. Similarly, you can say if I provide 1 kilowatt of photovoltaic, that much energy is generated, so that is offset. So you can make comparison, where is the you will getting the more payback, whether you are able to get the more payback with the energy efficiency or renewable. Now net zero energy building. So what is net zero energy building is, so any building, it will consume energy because any activity we need energy. So energy will be consumed. So first thing is we need to try to minimize energy in building, and whatever energy that now we cannot minimize, we can offset it with renewable energy systems. So if we provide whatever net energy consumption in annually is there, if we can use the on-site renewable energy system and we can make it zero. So this building is called now net zero energy building. So let's say your in base design your building energy consumption is at 100% level. So first thing you can try to bring it down with different energy efficiency measures. So if you apply different efficiency measures, it will bring down here. Now if you say it's very difficult to bring it down now, so whatever the reduction is there, so that you can offset with the photovoltaics or the small wind system to make it net zero. So if it is, this is conventional building, first you try to internal load, external load, ventilation load, shading, daylight harvesting, natural ventilation. So all things you can do and bring your make your building high performance building, and the remaining thing you can offset with RE systems. So here is net zero example, the example of the net zero university, Nalanda University. So you can get the more information on this, their website, nalandauniversity.edu.in. So they were able to make their building high performance building. So their baseline consumption was 160 kilowatt hour per square meter. And with use of the different strategies like daylight strategies and the micro passive strategies, they were able to bring their consumption down to 50 kilowatt hour per square meter. And the rest of the 50 kilowatt per square meter, kilowatt hour per square meter, they are now using generation with the photovoltaic and biofuels. So they are able to make their building net zero, and they are net positive, 5 kilowatt hour per square meter. So here is the end of last slide. So here is a quote from GRIHA existing building, GRIHA for existing day schools by Dr. Ajay Mathur. Children are our greatest resource for the future, and schools are the facilitators for inculcating knowledge and values in them. Schools therefore present a great opportunity for driving change towards sustainability in our communities, sanitizing young minds, and presenting models for transformation. Thank you.
Thank you very much, Aviruch. I think super fascinating and informative session filled with lots of inputs, that people can take at different levels if they want to become energy efficient.